Let's now move on to the last operation on the binary search tree, which is about deletion. And I would like to point out right away about the input parameters that we have to define for this operation or this method. And in order to delete an entry, all you need will be the search key. You don't really need the element value over here. So this should be done by contrast with how you did it for the insertion. Let me show you. If you go back to the slides for insertion, whenever we want to insert an entry, you have to pass the key and the value. So the value somehow has to be set as the element value ultimately, but that's not the case for deletion. And more precisely, if you go to the source code on Eclipse, you can see, so these are the two exercises you're assigned to do, one for insertion, the other one for deletion. And for both of them, of course, you have to pass the root of the binary search tree. That's a must. And apart from that, in the case of the insertion, you have to pass the search key to really search for either the internal or external nodes to insert, and then also the value. But in the case of the deletion, you only need the search key over here, because once you identify the node you want to delete, if that exists in the tree, in that case, just delete it. You don't need the data value anymore. That's something I'd like to point out right away. And for the deletion, it's actually more trickier than how you should do for insertion, because we got different cases to consider. Remember, we actually got 2 cases for the insertion, but we got 4 different cases for deletion. So that's why maybe I should really go with the principal presentation and the visual illustration side by side for each case. Maybe that's the best way to present. Let's try with that. Right, so let's say we are still trying to call the search routine. So this is really the foundation for all the 3 operations. So you want to make sure you understand the search routine very well. If you got any doubts, you should really refer to the earlier part for the lecture. Let's say we want to call the search on the search key over here. You can see the K, so that'll be the input over here. And P will be returned. And P can be internal or external, as we know very well. Let's talk about the 4 different cases. Case number 1. What if the node P is actually external? What does it really mean? That would mean the key over here as the input doesn't really exist in the tree. In that case, do we have anything to delete? Well, in that case, no. So key does not exist. In that case, nothing to remove. That's the first case. Very straightforward, but it's still worth illustrating very quickly. Right? Think about the case number 1 over here. Right? This is case number 1. For the other one, you can disregard just for now. For case number 1, let's say given the same binary search tree that we're familiar with, let's say I want to delete the entry with the key 31. Let's say that's the one I want to delete. I want to delete 31. So start from the root. 31 is less than that, so we should go to this left subtree. And also 31 larger than that, so we should really go to this left subtree. 31 less than that, so we should go to the left subtree over here. And also 31 larger than 28, so we should really go to the right subtree. And the 31 is larger than 29, so we should really go to the right subtree. So this is really the P that will be returned. Right, so this will be the P that will be returned from the search routine, P. But since the entry with this input key 31 doesn't really exist, do we have any entry to delete? The answer is no. It wouldn't make sense to just delete this external node, right? So nothing to delete. The conclusion is nothing to delete, right? That's about case number 1. Let's now move on to case number 2. The assumption is if we move on to case number 2, that would mean case number 1 is not the case, meaning that it is not the case that P is external. So what does that mean? That means P is internal. And given that P is internal, we can subdivide that into different cases based on what the shapes are for their child nodes. So that's why for the remaining 3 cases, case number 2, 3, and 4, is really about subdivide about the situation for P being internal in terms of their child nodes. That's something you can keep in mind. So for case number 2, we say that P is internal and also the child nodes for P are simply external. This will be the easiest case to really handle. Let's talk about it. In this case, we call that there will be no orphan subtrees to be handled. What does that mean? You'll be the best to illustrate when I move on to iPad and show to you visually. In that case, we can simply detach the P from its parents. That's what we can do. We don't need to do any further compensation. And by compensation, I meant something which I will illustrate maybe a little bit later. But for case number 2, it's rather straightforward. Let's now take a look. And now let's now switch to the diagram over here. And let's now talk about case number 2 over here. And you can still disregard this part over here for case number 3 later. Let's say we want to delete over here. Let's say we want to delete the node 80. Let's see where 80 is. 80, we start with 44. 80 is larger than 44, so we should really go to the right. 80 is smaller than 88, so we should go to the left. 80 is larger than 65, so we should really go to the right. 80 is less than 70, so less than 82, so go to the left. 80 is larger than 76, so we should really go here. That's where we are. This will be the P that's going to be returned. Right, so this part over here, this will be the return internal nodes from the search routine. This will be the P. And you can see, in this case, you can see very clearly visually. If I want to delete this particular node, how easy is that? You can simply just detach this particular reference over here. You can see there is a child reference over here from 76 to here, and also there should be some another parents from this node to this node over here. You just have to set those references to null. That's all you got to do. And what does it really mean? The phrase over here. When we said there's no orphan subtrees to be handled. When we say orphan subtree, let me just mention very quickly. Let me define that, and then we'll see exactly what it is in later cases. So, orphan subtree, by definition, it simply means a subtree rooted at an internal child node. It is a subtree, and its root is actually an internal child node. And why is this notion of orphan subtree important? Let's see 2 examples. Example number 1. If I want to remove this parent node over here, and in that case, the left subtree over here is so-called an orphan subtree because the root is actually some external child node. In this case, it would be okay if I simply detach this parent node over here directly from its parents, in which case, these orphan child nodes over here, since they didn't store any meaningful data anyway, so in that case, we can just get rid of this link. That'll be okay. On the other hand, let's say we want to remove this particular parent node. In that case, we have to do some compensation for the reason that if I simply try to detach this node from its parents over here, for example, in that case, this left subtree and also this right subtree over here, they are orphan subtrees because they are both internal left child node and also internal right child node. In that case, if you didn't do any compensation, let's say I simply get rid of this node and get rid of this link, what's gonna be the result will be I got one tree over here, I got one tree over here, and also I got the remaining part of the tree. In this case, I got 1, 2, and 3. 3 trees that are somehow not connected to each other in a meaningful way. So that's definitely not good as a consequence of the deletion. So that's why the notion about orphan subtree is so important. But I think I'm just trying to sketch as a look ahead. But later on, we're going to talk about how we can handle orphan subtree like these over here. Right, let's now complete our case number 2 quickly. We just want to remove this node, in which case the 2 orphan subtrees will just be okay without any compensation. So what we're going to do is, let me be careful over here. So conceptually, what you should do is you want to delete this particular link over here. That's what you want to do. And then it's kind of up to you. You can simply delete the link, and then you simply create some external nodes over here as the new right child for 76 because you want to delete 80. So conceptually, you really want to delete this part over here, let it be garbage collected, and the way to do it is to remove this link, number 1, and also create some external right child over here. That's what you can do, right? Of course, it could be that maybe this node over here could be maybe the left child of another node, in which case you would do something symmetric. So that will be up to your implementation. Let's now move back to the slides. And so that's about the operation I just illustrated for case number 2. And there will be a very important question over here. every time you try to modify the structure of your tree, for example, you may want to do some insertion or deletion, you always want to ask yourself this question. Is the resulting tree, in this case with one less node, is it still a binary search tree? And the way to judge it is by checking it, right? Let's now take a look, okay? We are only removing this particular node over here. In that case, is the resulting tree as a binary search tree still? The way to check it is to see if it still satisfies the search property, or you can just do an in-order traversal to actually see whether the resulting sequence is sorted. That'll be different ways for you to check it. But let's think a little bit more logically. If I want to do an in-order traversal, after 76, it used to be that I should go to the next one for 80, right? That's for in-order traversal. After 80, I should really go to 82, right? If you look at the structure of the tree. After 76, I should really go to 80, and then I should really go to 82. Think about the sequence over here. Used to be the in-order sequence is going to be 76, followed by 80, and then I will go to 82, and then etc. Right? So these are the three nodes I'm talking about in terms of the in-order traversal. If I simply remove the 80 over here, the resulting sequence is guaranteed still to be sorted. So that means I'm not really destroying the property. I'm not compromising the property for the search. I'm not compromising the search property for the binary search tree. It's very important for you to know, right? So the conclusion is still a BST with one less node is really important for you to see why this is the case. Okay, and the way I try to illustrate it is to think about how you would have done the in-order traversal. In that case, you would just remove one intermediate node, and the similar way of arguing should be applied when we talk about later cases. We'll get there. Okay. All right, so now we are done with the case number 2. Let's now move on to case number 3. For case number 3, so that means the P over here is actually internal, given that it doesn't satisfy case number 1. However, P's child nodes are not both external, meaning that maybe one of them is actually internal. That might be the easier case to handle before we talk about when both of P's child nodes are internal. So let's talk about case number 3, which is, let's say one of the P's children, let's say R, is actually internal. So that's actually a little bit trickier than before, but we're gonna handle that. Okay, what should we do? If one of the child nodes of P is actually internal, we got to do some compensation. But what kind of compensation do we have to do? We got to be careful over here. We can actually remove it. Let's say R's sibling is actually external because R is the only internal child. That means its sibling is actually external. I'm going to visualize this in a moment. Let's just go over some principle quickly. In that case, we're going to replace the node that we want to remove by R, right? Sounds easy, but let's see exactly how to do this. Let's now move to the case number 3. Right, so let's now look at this diagram over here. And let's say we want to remove the entry or the node with the key 32. Right, let's see where it is. So we start with 44 over here. 32 is less than that, so we go to the left. 32 larger than 17, so we go to over here. Right, so now we found it. This part over here, let's now identify it as the P that we talk about. Right, so this node over here is P that we search for, right? And let's now take a look at the structure. This will be the left subtree. This will be the right subtree. You can see one of the child nodes is actually external. The other one is internal. That's exactly the condition for case number 3 over here. And let's also try to name the R over here. So we say that we want to name the internal child node to be R. And then we're going to replace the P by R. Let's now name that internal child as R. Okay. You can see the internal child that we talk about is over here, right? The 28 over here. So this one is the R that we talk about. And in order to see exactly what to do, why don't we apply the same reasoning as before? We want to see what the in-order traversal it is, right? Eventually, we're going to impact this node that's to be removed, and also its parents, and also the child nodes that we need to worry about. And for this child node over here is external. It will be bypassed anyway in the in-order traversal, so we don't need to worry about it. Okay, so why don't we try to look at what's going to happen? I can show you a little bit more in terms of the sequence over here. Right, Why don't we go from, let's say, from the beginning? Okay, so we go from 8, 17, and then 21, 28, 29, and also 32. And after this, we actually get to the 44, and etc. Okay, let's think about what's happening over here. Let me just do a little bit more annotation over here for you. You can think about this part here is the subtree for that internal child. 21, 28, 29. So this is that particular subtree. You should really think about this particular subtree as a complete whole. And we got the root over here. Sorry, not the root. The parents of the node that's to be removed is actually 17 over here. And then also we got 32 is actually to be removed over here. And this is the internal child that's actually that's going to become the orphan tree before we do the compensation. And the 44 is actually what goes after the node to be removed, right? You really want to try to see the correspondence of this part of the tree over here with the sequence over here, right? And the remaining part is not going to be impacted. So that's why I don't draw them. It's very important for you to also try to draw this sequence yourself to see. For now, I'm just going to illustrate to you directly. Go right to the point. How do we remove 32 over here? How do we remove it? If you want to remove it, of course, from the sequence, you just want to remove 32. That's what you want to do. However, to do it, you want to make sure, in order for the resulting BST, the resulting tree still be a BST, you want to make sure 29 will actually follow right before 44, right? You want to make sure the 29 over here will go right before the 44. To do that, this one turns out to be easy. This is what we can do. Let me show it to you. You want to, first of all, detach this particular node from its parents. And then you want to let this parent over here, which just lost, it's a right child node. You can simply relink over here. So there are two things you want to do. Number one, you want to detach the node you want to remove, right? And then you want to attach the right child of this parent node to the internal child node of the node that's to be removed. Right? I try to be very careful with my wording, so you may want to rewind the video if you got any doubts. Okay, so these are the two things we want to do. After this, what we will get is we got this particular tree. Let me just try to highlight it in yellow. The resulting tree will be something like this. We got 8 over here. We got 21. We got 28. We got, oh, let me do it again. Beg your pardon. So we got, let's try to do in order traversal on the new tree once more. We got 8, and then we got 17, and then we got 21, and then we got 28, and then we got 29, and then we got 44. Whereas this node over here has been removed already, right? So we are still maintaining the search property for the resulting tree. So that's still a binary search tree, right? It's very important for you to see, number one, to see how to make the necessary changes when you do the implementation as the exercise. Number two, which is equally important, is for you to see the resulting in order traversal is really like the corresponding in order traversal. We are only just removing the 32 over here, whereas after 29, we still got 44. So after 29, we still got 44 as the next one. Right? It's really important for you to see that. And for case number 4, we're still going to apply the same kind of reasoning. There's one more hint I would like to give to you for your implementation. And you may have been wondering about that. What about this link over here? So this is node to remove. It used to be its internal child node. In that case, we should also detach this node as well, because officially speaking, after the removal, this node should not be attached to any part of the resulting tree. So if you still keep this link over here, that's not good, right? You want to remove this link as well. So this will be number 3, which I didn't quite mention before. So this one here should also be detached as well. So this will be number 3, and this will be number 2, right? So 3 steps. You want to make sure you properly set the references. All right, let's now go back to the slides. And the important question for every case will be, is the resulting tree still a binary search tree? As we argued before, indeed it will be. And the way we justify it is by using the in-order traversal. Alrighty, so let's now move on to case number 4.